Okay, so in a moment we're going to have Hugo Paquet speaking on semantic foundations for laziness in discrete probabilistic programming. Also, a note for people, not now, but when the session is done, please put up your posters if you haven't already. But please wait until the end of the session.
Okay, thanks, Cameron. Yes, so this is joint work with Simon Castellan and Tom Hirschowitz. Simon is here in the room. So let me just start by explaining a bit the context for this project. There is this large project called Botoscopia, which is led by Simon and based here in Rennes, actually, at Inria. And it's a project that involves computer scientists, but also plant scientists, and also people who are not academics who so there are organizations that work with kids, there are organizations who care about more practical aspects of plant science. So what the project is they are building and maintaining a large database of plant species, which is structured in a particular way. And then from this database, they are building tools to automatically generate things like teaching materials or activities for kids or identification activities for people. But so overall, the goal is really to get people to engage more with specific features of plants and really understand how to compare species and so on. So these are the applications. I won't talk about that, but I'll talk a bit more about the I suppose the database aspect and the structure of it, which is related to probabilistic programming. So here's an example I made up. You have a type, so this is a type, this is not a species, it's a type of species called flower with a record type. It has color, size, and season with possible values for each of them. And once you have a type of species, once you have a type, you can write a species. So my species would be a probability distribution, so a probabilistic term of this type. I'll give you an example. So the color is randomly either blue or red with a probability. The size is similarly either small, medium, or large with a certain probability, so you write a program. And the season is deterministically winter. So this is probabilistic, and this corresponds to something called species polymorphism I think in botany, where two individuals in a given species can have different traits, and so there's an understanding that it's not all individuals are exactly the same. So if you understand this probabilistic program as a distribution, of course it's just a distribution over this large algebraic data type, and so you can represent it naively in this way, right? Values and probability coefficients. Or you can represent it slightly differently in this way, observing that each component is defined independently in this case, and so I can define each component of the record type as a kind of probabilistic tree, where there are Boolean variables that are corresponding to the flips with a certain bias, and then output values depending on the value of these variables. Now, this is one possible way to implement flowers, but in applications of the Botoscopia project, sometimes they care about other ways to represent the same type of species. And so there might be a simpler kind of representation for flowers, which just remembers the color and the size, and the size can only be small or large. So we're going to care about ways to translate from one representation to the next. So there's there's probably many possible translations, but one is to just get rid of the season field, and then depending on the size, so obviously if it's small or large, you can keep it as small or large. But if it's medium, maybe you randomly say it's small or large. And so this probabilistic is not just to be able to talk about probabilistic programming, is because it's important that if a kid is engaging with the tool, then they see a medium-sized plant, they might half the time say it's large, half the time say it's small. So it's important to care about both options. So you write a probabilistic translation, which I hope you can see is a probabilistic program. So it doesn't really matter how I implement it, but it's just what I said. It's a program of this type. And so what's interesting is to look at the ways to compute, so the method for computing the translation of a given species, depending on the representation that you choose. So of course, if you choose the naive representation, the only way to compute the translation is just enumerate over all the possible values, apply the program, and just reorganize the distribution. If you start with this representation, it's a little bit easier. You just get rid of the winter field. And then, because I said that when it's medium, it becomes small or large with probability a half, you kind of expand the tree with a new random variable. And then you reorganize the structure so that there's only one path to small, one output node for small and one for large. Okay, you might recognize this as this idea called knowledge compilation. This is a binary decision diagram valued in a particular set. And it's, I think, a more broadly known idea, but the most popular instance of this kind of knowledge compilation is in the DICE language, which is from a few years ago. So I think that's maybe the most well-known implementation in this community. And what we did in this work was to understand knowledge compilation as a particular evaluation strategy. So there are two main ideas. The first idea is to realize that sampling is actually two effects, or at least you can see it as a composition of two effects. First, generating a new random variable, and then later on reading the value of the variable you've generated. Okay. So this is not our idea, so a few people have taken this seriously already, including at LAFI last year. The second idea, I think is new, although I'm interested if you've seen it somewhere else, is to decouple these two effects and evaluate one in call by value and the other one in call by name. And I'll explain, well, try to explain on one example why this is the right thing to do. So look at this simple program. It samples a Boolean variable and just returns the pair of the duplicated pair. So really in probabilistic programming, this should always return either 0, 0 or 1, 1. But that's not really the BDD, the knowledge compilation representation. You would really have a pair in DICE, for example. You would have a pair of BDDs. But what's important is that the Boolean variable that appears in each of these diagrams is the same, right? If this one gives 0, this one also gives 0. Okay, so why does this correspond to this? If I was doing both effects in call by value, I would just have one variable and one single diagram with one probabilistic choice, and then at the end a pair 0, 0 or 1, 1. If I was doing it both in call by name, I would have two diagrams like this, but the variables would be independent, so there would be no correlation between the two copies. So this is really what's going on. And we tried to explain this using standard semantics methods. So nothing really is new. So there are two monads. One monad is for name generation. One monad is for reading the value of the variables you've generated. The name generation monad is exactly the one that appeared in the previous talk, although it's a slightly different base category, but really is the same idea. What's important for these monads is that the semantics is indexed by a finite set of variables, so you want to keep track of the variables you've generated so far in the execution. And then you just apply really the standard thing. So if you haven't seen this before, it might look a bit cryptic, but really, given a monad, there are standard ways to interpret call by name and call by value. So that's what happens. You have a call by value model for name generation, call by name model for reading. And we came up with this kind of way to combine them based on the distributive law, which is a standard way to combine monads. So it gives you a kind of hybrid model where the types are kind of call by name types. That's why the types are diagrams. And the terms are more like call by value with respect to name generation, the same as here. I'll say just to illustrate what's happening here, if you don't understand this. So you have to understand each type as essentially a set of kind of layered decision diagrams, which give you situations like this. So I think this is exactly what happens in knowledge compilation. So, but the point is really it comes for free from this semantic model and these well-known ideas. So for some types, you create a new layer by saying I read, and then depending on the value of the variables, I return either a diagram for the left or a diagram for the right. And this should be a times. For product types, you just return a pair of diagrams. But they're over the same set of variables, which is why you can have correlations. Okay, so just briefly, so R is implemented in call by name, but this gives you the same as call by value, because R is essentially doing nothing. It's just reading the state, and it doesn't matter what order you do it in. It's a very kind of a benign effect. And so essentially call by name is equal to call by value, which is why this model gives you the same in a precise sense as the usual call by value semantics of probabilistic programming. So just to summarize, knowledge compilation can be seen as an evaluation order where you decouple the effect into two effects, and one's in call by value, one's in call by name. And I think generally it gives you a new perspective on call by need more generally, maybe for other effects or for other kinds of types. Okay, I'll stop. Thanks.
Thank you. We have time for a question or two. Yeah, please set up.
Thanks for the talk. So can your framework support higher order and bounded loops, control flow, and things like that? Maybe you said it and I missed it, but...
No. So control flow, as in branching, yes, because you have coproducts, sometimes. But we haven't done recursion. I think recursion would be maybe the easiest. High order is... It's not just a tree, right? There's going to be functions at each level. So
one of the cool things about lazy people is that you can generate like elements of a type that depend on like infinitely many random values. But it seems like if your name generation is called by value here, you wouldn't be able to do that, because you could be lazy about reading from the infinitely many, but you still need to like allocate infinitely many names in order to do that. Does it still work? Like, can you still sample a Brownian motion?
Lazy people, there is some call by need happening, right? Because even though, depending on some of this kind of encoding is happening in Haskell behind the scene. So maybe it's hidden in a different place in a way. But let's understand.
Yeah, let's thank the speaker again.